Greetings and felicitations to all. So I figured I need to post something, and I have been doing work with the electronic stuff, so I guess I'll get this out there. And so here we had a coil. This was printed on the last printer that went kaput, and then that one, too much electronics and not very sturdy. And then this is the bottom of the line Ender 3D. It was cheaper than that one. It was less than $200, and it came with a full roll of filament. And it took a little bit of fiddling with, and you have to manually balance the bed. It's kind of fun doing all the tinkering, although it would be nice to have an auto-leveling bed. The prints are way better. I mean, it's just much more precise, much cleaner and whatnot. But to get back to it, so it went from, say, that length of wire on here, and then on here, and then on here. And you know, the other reason I'm not really been posting too much is I'm just, you know, I'm confused. This electronics stuff is like, golly, this stuff's complicated. So, but I am confused, and but I can show you some neat stuff. Although it's just going to be, you know, on the test bed. But there are a couple neat things to show. But really what I did, so I would take this and then like here's the data for that from an LCR meter, and coil 1, coil 2, coil 3, the inductance. I'm looking at it at 120 and a 1 kilohertz sample rate. That might be a little bit of overkill, but you know, seeing as I'm flying blind and don't know what I'm doing, I'm just gathering everything. And then the resistance, and it's a little funky measuring resistance with an LCR meter because it seems to vary a little bit, but the standard voltmeter is not precise enough. It would only go to like 4.7, and so this is much more precise. And then the capacitance of the coil, I don't know, you know, Tesla help me, I don't know what the heck what the heck that really is getting at. You can see how dramatically the capacitance changes based off of the sample rate of the AC sine wave between 2.6 UF and 125, and that doesn't factor into, you know, your frequency in an LC tank circuit. But I'm getting off base there. And so one of the things I wanted to do was to track the induction and those other parameters, mainly the induction. The resistance shouldn't change. Going from this coil shape to this coil shape to this coil shape. And so we'll leave this stuff out. That's that. And then we go to this coil. And so let's take, I guess coil 2 is the best one. This one seemed to have more splices. And we go to coil 2, and we see that the induction jumped. Same length of wire, but you're getting more induction for the same resistance. And then I've measured 2 of these, which is now, you know, more flat and more wide. And the induction has, where's the mouse? The induction has jumped again, not as much, 11.449. From 11.055 from 10.245. But you can see that the induction for a given length of wire varied so far from 10.24 to, what did we say, 11.4. And one thing that does go as I expected is that if you're then just charging a coil to a set voltage, as you increase the induction for a given length of wire with a single air core solenoid, it charges more efficiently. So if you like ran the machine off a cap, the cap goes down less for charging another cap from 0 to 10 volts when you have this at 11.449 versus 10 whatever it was before. It's not dramatic, but it's there, and that makes sense, and that's good. And so I'm happy about that. So you can start to see, if you have a single coil like this, if you want an efficient DC-DC converter, this would be a good way to go. But then I've also been thinking about, it's out of focus. When you have two coils wired together, are there things that you can do with that? And so that's what this is. And part of it makes sense that if you wire two coils, well, actually, even before I get there, and this is one of the things that's confusing to me, and I'm sorry just to kind of be talking here, but that's what I'm going to do. So if we go with Faraday's law, that the strength of the magnitude of the electromotive force, the voltage of the electromotive force, but again, it's a field, is proportional to the rate of change of the magnetic field. So, a strong magnetic field changes quickly, big EMF, weak magnetic field changing slowly, small EMF. So my first kind of go at this would be that the best thing you want to go for is the most inductance for the least amount of resistance. And so here the inductance is 9.3 millihenries, 4.77. So I divide with those two and I get, 1.988. And then that improves, as we go forward. Now it's, just with a single coil looking like that. And I'm seeing improvement with charging the coil. But if we go back to a different spreadsheet, here when I had this big 10-pound coil, and it's thicker wire too, and it's 10 pounds. So now instead of 10, 11 millihenries, we're at 95.5 millihenries, and instead of I think it was 4.4 ohms, whatever, we're at like 5.9 ohms. So you divide the inductance by the resistance there. That ratio is 16.18. Where am I? Versus 1.98. But that 10-pound coil, it does better than one of these, but it's not like spectacularly better. So that's sort of a mystery to me. And a further mystery, with those solid state relays, they're rated to be able to switch at a maximum speed of 100 UF, 100 UF pulse. I find that they actually continue to improve a coil like this down to 60 UF. With the 10-pound coil, it kind of tops out at about 120 UF, and then it stops improving. So in other words, if that 10-pound coil kept improving, then it would be, I think, a more dramatic difference. So you have something like with these two, as I'll get to in a minute with these different arrangements, I'm getting something with these two, which maybe weigh a pound or two versus 10 pounds, which is nearly as good as a pound or two versus 10 pounds. So it's nearly as good for 1/10 or 1/5 the mass. So why, again, I don't know why that is. If you're looking at it strictly the inductance over the resistance, I think, just to throw it out there, I think there's a couple things. It might be skin effect, that thicker wire, the skin effect begins to become very predominant, at around 100 UF, and maybe I can find some equation or something to try to see if that would fit. The other thing is maybe the Arduino isn't given a clean enough pulse, and I've been thinking I need to perhaps learn how to build a gate driver to drive a MOSFET, but I have those prepackaged SSRs. I don't suspect that's the problem, but maybe if I had to go with one, I would just say skin effect. But really, I don't know. That's what I'm saying, is I'm flying blind, just out there. A second thing, which I'm trying to process and understand, is again going back to Faraday, that it's rate of change of magnetic flux, giving you the magnitude of the EMF. So if you have two coils in series, the inductance doubles, and which is this coil 2 and 3 in series. So those two double, this doubled. The resistance is, it's twice the length of wire. The resistance doubled. Yet when you're pulsing to charge a cap, these two in series do better than each one of these individually. But you would think, all right, twice the inductance, twice the strength of the magnetic field, twice the resistance, it changes half as quickly. They should be identical, but they're not. This is better. And I'm trying to wrap my head around that one too. I don't know. But then where it gets fun is you can think of putting, instead of them in series like this, and then, I also just hooked them up in parallel, but I didn't see something on the LCR meter that was all that strange. But then you can also think of the two coils interacting with each other and then how they're wired together. And depending on where you wire them together and how you have the coils, you get a big difference in inductance. So in one case, the inductance begins to cancel out, and in the other case, it's adding. So there's a couple things there. First of all, I think I had it backwards in the last video. This one is the bucking. I'm saying it's the bucking there. It's kind of, I remember taking biochemistry in med school and like staying up half the night with these notes. And it's like, I can't figure out, that arrow's going the wrong way. And so is that one. And then you go to the lecture the next day and the son of a gun's just, oh yeah, those arrows, they're all, I had those wrong. I think he was just doing it to be a dick. But, so I don't mean to have been a dick about this, but I think this is not the bucking. This is the counterwound. This is the bucking. Because when they're bucking, you see the millihenries go down. And I'll show a dramatic example, two progressively more dramatic examples in a moment. So that's wrong. I think that I would label that counterwound. I would label this bucking. Then the next question is like, well, are you actually doing anything here? Or is it just because, now it's shaped like one coil? But we have this full length of wire and, you're at 20.48. And then, with it like this, we know that this shape, because, we've been gathering going there, is actually inferior to the other shape. So it's not simply that they're sitting like that. It has to do with the way they're wired counterwound, and that becomes more apparent in a moment. So just that was this page was two of these blue coils, and so there's not going to be good magnetic coupling because the bottom wire here, these, or I think like 1 1/4 inches or 1 1/3 inches, is going to be like 2.5 or nearly 3 inches from the top wire of the other one. Or here we're down to 0.75. These were 1 inch. So now what I did here is I just took this 23.76 minus what it was in series, was 3.28, and then divide that 3.28 by 20.48. So this was 16% better wound this way than just the two in series. And when you put it pulsing and charging a cap, you actually see an improvement. So it's like when I see an improvement there, it's like, okay, that's good. Now if we go to the next set, you see that because we wound the coils in a different shape and no crazy kind of Mobius strip coils or anything like that, just air core solenoids, but we're getting this improvement. And now when we put the two in series, it's 22.03. It's that when it's bucking, and it's now that 27.1 versus this. And so now we've gotten a well, let's do it, a 5.24 difference in millihenries between the two. And so now, give me a second, equals this divided by the 22.03. Okay, that's what I just did there. Anyways, so there's a 23% improvement with these two coils. Now, I don't have the third coil wound, but I did look at this last night. And so now we go to sheet 3, and this is just coil 1 and coil 2. And I haven't put everything in the spreadsheet yet. Well, I did. It's not clean. But it's 22.16 in series, and now it's 29.15 in the counterwound and 15.24 in the bucking. And that's because we're getting closer to having a bit better magnetic coupling. And so now it's a 31% improvement. And I'll just show you that real quick. Okay, so for some reason it's reading 21.9 instead of 22.16. Maybe it's how well the alligator clips are on there, but that's not the real thing. The real thing is when I take this and I'm going to put it now on top there. Now we went from 22 to 29. Let me get it centered there. And now I've put a hole all the way through these coils, so I'm also going to be looking at iron cores, welding rod cores as well. Just, that'd be a way to put some more magnetic coupling in there. 29.09. Now, these plates holding this are 3/32 of an inch. I'm going to see if I can get away with 1/16 of an inch, because if I just even like press down on this, you can see just getting the magnetic coupling a little bit closer, and you're getting that. Now if I flip it over, this is the bucking. We went from 22, if it'll stay. Oh, it's the wires want to stay. Down to 15, 14. And if I press on it, even lower. And this one's got some wires that, that's where the wire's coming out of the coil, so it's even a more dramatic difference when I press on it. So this is not simply that, now the two fields are interacting. It has to do with how you hooked it up. And that would be when it improved in a counterwound, when it did worse in a bucking. Now the bucking actually stinks for gathering a radiant when you're just pulsing this coil. I think the way you use bucking coils is as secondary coils, and you still have all the magnetic flux going on. It's just going one direction. And if you're pulsing the coil directly, I don't think you can get at it, but I'm pretty sure you can get at it with secondary if the bucking coils are secondary, and I think there are interesting things that you can do with it. But this is actually the counterwound. Again, I don't really know what I'm talking about, and even if I do, I might label it wrong or something. But if we go back to Tesla's counterwound pancake coil, and I think there's kind of two ways that you can look at it. And one way is your friendly little electron is starting here. He goes round and round, comes out to there, and then he goes back, and now he's going round and around, and it's again in the same direction. It's not like it's going in the opposite direction there. Both times they're going in the same direction. And then he comes out here. I mean, there's not any, I don't see how there could be any handedness or chirality there, if I'm not mistaken. But they're both going the same direction. So that's one way of looking at it. But I think the other way of looking at it is that you have to consider it in terms of the positive and the negative and what's going on between the two coils there, and that as soon as the connection is made between here and here, there's a potential that's understood across the whole coil, and that these two coils are opposite in terms of their potential. And you see in his patent, he's saying that there's, instead of a minute difference between each wind with a single wire, you know, if you're going from like 10 volts to ground and you have 100 turns, after one turn the voltage has gone down, what did I say? Let's say 100 volts and 100 turns. After one turn, it's gone down 1 volt or 1%. And so there'd just be a 1 volt difference. But here, it's in relationship to what the two winds are seeing in terms of the ground. That's why I think you get that improvement. And I'll show you something else here real quick. So, you know, you can think about this, and it's like, that's neat, it's a flat coil. But as we go more flat with this, I bet we're going to see that that's not the ideal for a single length of wire induction, but we're going to get better magnetic coupling, so on and so forth. But, you know, you could think about, well, if you set this up, you know, like a crystal of salt, you know, where each line in multi-layers is equally spaced from all others around it, then you could have a multi-layer instead of being pancake and still counterwound. And then it's like, well, how precise does that have to be? So here's something just out of, you know, just out of the box. It's still got the plastic there. This is just the shape it came in. And I'll show you this. So this is just speaker wire, bifilar. And, you know, once you get away from where I torn them apart, they're just adjacent to each other. And so I've taken one line of the speaker wire and we put it on the inductance meter, and it's registering 833 microhenries, so 0.83 millihenries. Now, if we hook it up counterwound, no, let's hook it up bucking. So now it's hooked up bucking. Oops. The inductance, we said 820 or 831 microhenries, is now down to 19 microhenries. So the inductance is basically gone from this coil. And an interesting thing is, if you pulse a cap through it now, you don't get a, you know, like an inductive spike to gather off, but you also don't get any impedance or reactance from the coil. And so you give like a 100 microsecond pulse and the cap is pretty much discharged, because all it's seeing is the resistance of like you know, an ohm or two. So that's, and I would say that's bucking, and there are these fields, but they're now, you know, it starts off one way and then it ends up the other. And the way I think that people take advantage of that is, again, with this as a secondary, although, say it a third time, I'm kind of flying blind. But here's the next thing. Well, just real quick, again, one wire here, 834 microhenries. So now it's hooked up in a counterwound arrangement. So remember, with one of these wires, it was, I can't remember, I think 846 or 836, something like that. So when you have two of them now in series, then the coil form hasn't changed. It should be double the induction, so 840, like 1.6 or 1.7 millihenries. But when you actually look at it, it's 3.32 millihenries. And so now, instead of like on the spreadsheet where you were seeing like a 30% improvement most recently, now you have a flat out doubling of the inductance for a given length of wire than what you would expect just with it in series normally, because of how you're arranging it with this arrangement. And you do see an improvement as things go along. So it gets a little strange to think why that's any different than just a single length of wire arranged like that. But again, it has to do with the potentials that each wire is experiencing. And so, you know, like if you're just thinking of it about, you know, like an electron moving along here and all that, then that's not really getting the whole story, because what that electron is experiencing is determined by the potential, which is set as soon as you make the connection between there and there. So that's that. And so, you know, I've been as I said, then just pulsing these things and determining the number of pulses to get to this from 0 to 10, and then seeing how much, you know, if you run it off of here for that number of pulses, how much that goes down with the different coils and the different arrangements and so on and so forth. I can maybe show you a little in the spreadsheet there, but I want to, you know, kind of end on a little bit of a hopefully interesting note for people. And this was something I can't believe that I never looked at before. So here I just have this coil. I need to change this one, rewrap it onto the other form factor. But you know, you take that coil, you pulse it 198 times with a pulse width of 60 microseconds, and this cap goes to about 10 volts. And then before I kind of show you the thing I thought was really interesting, so I'm just kind of keeping track of this with, you know, one coil in series and so on and so forth with the different coil forms. I didn't give a good job labeling it there, but then 20 volts and 25 volts. So let me see if I can find. So like this 9.36 would have been in the counterwound, and then at 20 volts we can see that the big cap, instead of discharging from 10 to 9.36, discharged from 10 to 9.375, going from 10 to 20 volts, and then at 25, 9.384. The equivalent, you know, I mean, it's discharging to 18.68, but you know, or 18.75. Divide that by 2 to make the two of them equal. And so we see it does better at 20 volts than at 10. It does a little better at 25 even. Unfortunately, I can't go over 30 volts with this setup. These SSRs are rated for 60 volts, and I kept going up to 50 volts, and I fried a couple of them. And then it finally occurred to me, this is a buck boost configuration. So when this one here goes to discharge into here, let's say you charge this one to 50 volts. It had 50 volts here, so this is actually negative 50, this is 50. It's seeing 100 volts, and that's why they were frying. So I can go up to 30 volts with this setup. So I'm looking at it between 10 and 30 volts. And then I have some like 200 or 400 volt SSRs, but then you got to worry, you know, what's the resistance in the SSR and so on and so forth. So before like going up to high voltage, you're trying to buy like 60 pounds of wire or something crazy. Just looking at this stuff. But here's what I wanted to show you, which I thought was cool. So as I said, we're pulsing this 198 times, and that's what makes that cap in the middle go to 10 volts. Now we'll move the meter. We'll move the meter to here. We're at 10.01. It should be 10, but it's hard to get it dialed in perfectly, so close enough. Now we'll just run it off that cap, and you know, you see me do this before, and it goes to 9.33. Okay, fine. But what occurred to me, and I can't believe, I don't think I ever looked at this before. If we just take the diode out, let me shut the power off. Take the diode out. So now, I mean, I could have pulled the cap out too. We'll do that too. So now, you know, there's no load. Oh, I'm going to leave it in for a minute. The diode's out. One leg of this is out. I don't want to destroy the thing. Power back on. If the thing's unloaded, what does this cap go to? We saw last time it discharged from 10 to 9.33 when we were putting power into here. So now we're going to do it again with it not loaded. .27. So isn't that interesting? When this thing is loaded, drawing power off, it draws less power than when it's not loaded. So at first I thought, well, maybe the voltage in this cap is somehow interacting with the impedance of the coil, So then I got the idea, well, let's just put in purely resistive load. So now I've connected back up the diode, and I put a 100 ohm resistor across where the cap would have been. So now it's a load with 100 ohms of resistance. And keep in mind, you know, the number of pulses is the exact same. The pulse duration is the exact same. And what does it discharge to now? So when it was loaded with the cap, this darn thing drifts a little. It was went to 9.33, unloaded 9.27. Now loaded with a 100 ohm resistor, 9.33, 9.34. And if you start putting a lot of resistance across there, like 10K, it starts going back down towards 9.28, 9.27. So that's pretty interesting, that this thing, the more you load it, the less power it draws. I mean, within reason, it stops at a point, but it draws less power loaded than unloaded. And it's funny that would be the case for like every single off-the-shelf DC-DC converter that you might pick up for $5-10. They draw less power when they're doing work. So I'm shrugging my shoulders behind the camera. So I don't know, as I said, kind of flying blind on this, but you see people talk about that now and again, and this is just another example of that. You also, like with the Bedini simplified schoolgirl circuit, if you have it without the really strong magnets, when you have those strong neodymiums, when they're spinning past, their interaction with the coil is going to overshadow anything else. But when you have just the really weak magnets, like he was saying to use to get a quick pulse, you'd also see that when you connect the thing, the rotor would speed up and it would draw less power. So now you can also see that on the desktop if you care to do it. So I've got a lot more work to do, and I'm going to wrap this one up, but I need to rewind this in this configuration. As I said, I'm going to look at it with cores. With an air core with this as a counterwound, I wouldn't be surprised if it does as well, this pounder to a wire does as well as I was doing with 10 pounds with a single coil. I'm going to have to see, and as I said, I don't understand all the variables at play, and I don't understand which ones might be from components and which ones might be actual things going on with the coil, and what all the things are that are going on, and so on and so forth, and blah blah blah. But now that I have a 3D printer again, I'm gonna go back at some point to the window motor and the pulse motors and have fun with that. But you can see how you kind of get on one path and then you have fun with that. And I am making some progress in terms of having something where the efficiency is close to what I was getting with 10 pounds of wire with 2 pounds of wire, and looking at that and seeing what I see. But I like that one where you can demonstrate that when it's loaded, it's drawing less power. Okay, thanks everyone, and talk to you later.